This is, in a nutshell, what Bacon has proposed. He says, identify the forms in nature. Forms in nature he refers to. An example is heat, light. Okay, these are examples of forms in nature, these phenomena that happen in nature. All right, heat, light. Okay. Now, practically, we're going to muster the instances. It's a term that we don't often use unless you're in the military. You don't hear that term muster very often. Muster the instances. This is to collect a list of all examples of the form and of times when the form is present or absent. Okay, kind of makes sense, right? Here we have light, there we don't have light. Okay. Here we have heat, here we have cold, which is not heat, or not very much of heat, or whatever. This is kind of the concept, right? So you're studying heat. You study heat in various forms and in various different places and things like that. Okay, he says that we should use the knowledge to gain power to change nature. So the idea here is identifying first, okay, what all is there in nature? What all forms are there? Let's go take a big sample, a big collection of data about these phenomena, and then we're going to use that knowledge as power. You know, the old saying, knowledge is power, right? Well, to some degree, right? To some degree it is. So once we know and understand these phenomena, these forms, then we can use that knowledge to do something, to manipulate, to change the universe. Okay?
Like an aqueduct system?
What's that?
Like irrigation or an aqueduct system?
What about it? Aqueduct system?
Well, I think it was the Romans or Greeks or whatever used, the water flow to have pretty much running water in their houses and kind of a septic system.
The septic part I'm not so sure about, but
Well, I mean, they had toilets and they had running water under it.
yeah,
So
okay,
they didn't
I see what
flush
you're
it,
saying.
they just
With the wash
Yeah.
a sewer type system. Well, I'm not really sure. I mean, are you saying that they discovered through studying
They're just
what?
using nature, like a river or a creek or something, to kind of push it in this direction, or
Okay.
irrigating fields or water crops, without having to tote buckets out there or something.
Okay.
Manipulating.
Manipulating
nature for
Yeah, they manipulated. I guess that's one way of looking at manipulation or something. Maybe a better example would be. Let's use the heat one. Let's talk about. Eventually they discovered heat came from electricity. Can produce heat in various ways, right? That's a more modern example, probably. Electricity can produce heat in various ways. Well, we can use that to, heat our homes. Or, I guess in another sense, you've got the water concept when in your car, hot water goes through your system and then it goes into a little heater core. It's like a mini radiator, and then air blows through that, and you get heat in your car. So that's an instrument. That's one way of looking at it, I suppose.
Heat comes from the sun. They used to have pipes of water on top of roofs to heat the water, so you can have warm water.
Okay. Heat the water by using sunlight on metal, run the water across metal. That's a good way of doing it. Okay. So there's an example of identifying a form in nature of hot water, like you're saying, and we discover that if you put metal here as a conduit and you have it exposed to the sunlight, it gets hot. Okay. This is kind of the general concept, what he's talking about. Does that sound like the way science typically gets done? Is that what you think that people are doing? Are they observing the same kind of things over and over again? Medical sciences, is that what they're doing? Are they looking at, well, this person's got cancer, that person's got cancer, this person's got cancer. Cancer, we could call that one of the forms, okay? We could say that's a form for practical purposes here. This cancer thing appears here, there, and everywhere, different places, and then there are certain contributing factors and genetic factors, so on and so forth, that cause this phenomenon to come into play. So as they observe what possibly are the causes, then they can work toward trying to find a cure, right?
I think at the beginning, because if you're observing it, it kind of makes you pose the question, why?
The why?
Yeah. Why does it do this? Why does that one do this? And that one doesn't do this? And what does this one do?
Right, okay.
And then you just kind of further on.
That'd be, back to the mustering the instances you have and you don't have. Why is it you have cancer here but you don't have cancer here? So, yeah, okay. All right, so I want you to really get a grasp on this basic definition of, when we're talking about science as a philosophy, okay, going about doing things in nature, think about this concept, and then let's talk about some other things here in a little bit. Theory and observation. Okay, this is kind of the old rationalist empiricist debate. You guys remember that? I know you've already been tested on it, and now it's file 13, right? You've already been tested on it, so you've forgotten that. Okay, Newton, Sir Isaac Newton. I know you guys have heard of Newton. You go down here to Mid-American Park. They have the little. It's called Newton's Cradle, I think is what that's called. It's got the little balls that are suspended. And anybody been there? You take one ball and you pull it back and let it go. It hits all the other balls, and then one comes out on the other side. You take two balls. It hits two balls. That equal and opposite reaction kind of thing going on here. Okay, Newton's Cradle. But Sir Isaac Newton, he discovered that Galileo's laws of terrestrial motion and Kepler's laws of celestial motion could be derived from his invention, calculus. Okay, he therefore unified them into a single theory of motion. So this is kind of what he does. He welds Galileo and Kepler together, and he comes up with the theory of motion. All right. He proposed a theoretical approach of mathematically, i.e. rationally, deducing a theory to base observation upon, rather than amassing empirical data as Bacon has proposed. So here's a little bit of a difference. He says, wait a minute, there's some things we can just do mathematically. We don't have to see this over and over and over again. We know enough that we can plug this into a formula and calculus will tell us if this is going to happen. Okay? Makes sense? Okay, we're all about work harder, not smarter, right? That's the old phrase. Work harder, smarter, excuse me. I got that backwards. Smarter, not harder. Maybe I do it that harder, not smarter sometimes, but the old saying is smarter, not harder. So he's trying to shave off all that unnecessary repetition and experimentation and observation and all that. And he says, no, don't have to do, just have to think. All right, and that's why I say it's kind of the old rationalist empiricist debate here, because which has more weight to it? The math? But the math corresponds to something, doesn't it? When you're doing geometry, for example, it corresponds to physical entities, right? Without that, So he's got that rational empirical thing going on here. Which really has more weight to it, though? By mathematically sitting down saying this will happen, or actually seeing it happen? Seeing it happen? Seeing is believing? Okay. We could plug into a formula and try to get, we could probably get really close to figuring out, if you have a set of tires on your car, we could probably plug in, knowing the properties of the tire, the roads, the distance, we could probably plug in some sort of a formula to figure out how long that tire is actually going to last just by using its properties and, looking at the weight of the car be on it for so long, so on and so forth. All this, it would get very complicated, I'm sure, but you could probably figure that out mathematically. But how accurate is that really going to be compared to just going out and doing it? Just driving the car till the tire pops.
I mean, they do, don't they? I mean, they have certain warranties and stuff like that on.
Well, they have warranties,
tires.
which sometimes they make it to the warranty, and sometimes they don't, right? Because they didn't, that exact tire, they didn't do any math. You know, this is a general, and all of the batches of tires don't come out exactly the same. They're not the exact same bunch of rubber and steel belt material and all that. So you're always going to have some differences. So we could get probably pretty close with a mathematical equation of figuring out this tire is probably good for 100,000 miles, whatever. But you go out and drive it and it pops at 102. Okay, which one was most accurate, right? The observation in that case, right?